Hello all, my name is Ashutosh Rastogi. I'm a teacher by profession. My mission is to impart quality education for all. For that purpose, I am creating these videos. If you appreciate my work, then please do like my video and subscribe my channel so that I could get the motivation to prepare more videos. Anyways, today in this particular lecture, we will going to discuss about the mathematical analysis of single tone AM signal, in which we will try to find out the general expression of single tone AM signal along with the power as well as the current content in our single tone AM signal. So these are the outlines. We are going to start up with the introduction, where we'll briefly discuss what we have done in our earlier lectures. Then we're going to describe the single tone amplitude modulation, what it is and what do we mean by a single tone signal, which will be followed by the mathematical analysis, in which we will going to evaluate the generalized expression for single tone AM signal, which will be followed by frequency spectrum, and then we will going to discuss about the amplitude modulated signal power distribution, that how power would have been distributed amongst the bandwidth, or you could say at the frequencies. Then we're going to discuss about the current calculation, what will be the current value in our AM signal, and finally we're going to conclude via discussing one of the important parameter of any transmitter, that is your transmitter efficiency. So in our last lecture, we have discussed about the modulation's general expression of AM signal and the modulation index. We had also discussed about the physical significance of the modulation index, that is what will be the impact of the value of modulation index when its value is equal to 1, is greater than 1 and is less than 1. Obviously we are talking about your over modulation, under modulation and perfect modulation case. So in this particular lecture, we will continue our discussion over the single tone AM signal and its mathematical analysis. So in generalized amplitude modulation case, what we have discussed so far is we will be having a product multiplier, in which we have to apply two signals. One is your carrier signal, and which is basically your high frequency signal, and second one is your information signal or message signal. When we are going to pass these signals through the product multiplier or product modulator, we are going to get the modulated signal, which is nothing but the frequency shifted version of the message signal. So general expression of AM signal can be given as ST is equal to AC cos of 2 pi FCT plus MT times of cos of 2 pi FCT, where this MT is nothing but your message signal and AC cos of 2 pi FCT is nothing but your carrier signal. So while just taking the common of this cos of 2 pi FCT, we can write it down as ST is equal to MT plus AT times of cos of omega CT. So instead of writing this complete cos of 2 pi FCT, we have just mentioned this cos of omega CT. So now we are going to discuss about single tone AM. So before we are going to discuss, let us understand what do we mean by single tone signal. So any signal which contains only a single frequency component can be termed as your single tone or monotone signal. So here in this particular case, our message signal will going to be have only single frequency like our carrier signal. So obviously carrier signal is also a single tonic signal, or it is only going to contain single frequency, high frequency signal. So just like our carrier signal, we are going to have our message signal also, which will only going to contain single frequency component. So here also the amplitude modulation process will going to be remain same. We will going to have two signal. One is our carrier signal, which is your high frequency signal, and just like your carrier signal, we will be having a message signal, which is basically a low frequency signal. But important point at this particular moment is our message signal will only going to contain a single frequency component. Okay, so when we are going to pass through this product multiplier, at the output we will going to get this modulated signal, which is your high frequency shifted signal. So this is the block structure of our single tone amplitude modulation system. Just continue with this mathematical analysis. So let us say that the three signals we are talking about are message signal, carrier signal and modulated signal. That is the signal that we are going to get after modulation process will be represented as your MT, CT and ST respectively. Obviously MT is for message signal, CT is for carrier signal and ST is for your modulated signal. So let us say MT as well as CT can also be given as MT, which is nothing but your message signal, that will be equal to AM cos of 2 pi FMT. Obviously this FM is only a single frequency component. In the similar manner, CT is equal to AC cos of 2 pi FCT. Here this FC also a single frequency component. So now hence the output of the product modulator will be given as, so obviously these two signals will get multiplied. ST is equal to AC times of cos of 2 pi FCT plus MT times of cos of 2 pi FCT. So on putting the value of MT, we have, since MT is equal to AM cos of 2 pi FMT, we just put it down in the last expression that we have got. So ST will be equal to AC cos of 2 pi FCT, which is nothing but your carrier term, and AM cos of 2 pi FMT. Instead of MT, we have put this value times of cos of 2 pi FC. So ST can be rewritten as AC times of cos of 2 pi FCT, which is nothing but your carrier signal, plus AC times of MA cos of 2 pi FMT multiplied with cos of 2 pi FCT. So as MA is equal to AM upon AC, so we can simply write instead of AM like your AC times of MA. So ST will going to contain this your carrier signal, that is your AC times of cos of 2 pi FCT, plus just in order to apply the formula of 2 cos A cos B, we have just multiplied with this 2 and divided by this 2. So we are having this 2 cos of 2 pi FMT plus cos of 2 pi FCT. So by simply applying the formula of 2 cos A cos B, what we are left with is your ST will be equal to AC cos of 2 pi FCT plus AC times of MA upon 2 cos of 2 pi FC plus FMT and cos of 2 pi FC minus FMT. So this is what I am talking about. Your final ST signal will going to contain three components. One is your carrier signal, one is your upper sideband signal, and second is your lower sideband signal. So in this particular case, we are basically not at all talking about a particular band, but this is basically your upper side frequency and lower side frequency, you could especially say, as it will going to contain a monotonic signal. It will not going to contain any band. So when we will going to discuss or see about the frequency expression, you will get to know what I am talking about. So this is your upper side frequency and this is your lower side frequency. Whereas in the generalized expression of our AM signal, we have just called it as your upper sideband and lower sideband. So this particular figure is basically showing the frequency spectrum of single tone AM signal. So this is nothing but our message signal, which will going to contain only a single frequency component, which is represented with this particular arrow, or you could say this particular signal. It is only going to contain this plus FM frequency, which is a single frequency component, and it's having this much amount of amplitude. And this is our negative frequency, its counterpart, that is your minus FM. So this is basically the spectrum of our message signal, which will only going to contain this impulse type of signal. So when we are going to pass this particular signal through the product multiplier circuitry, what we are going to get is, we will going to get this frequency translated or frequency shifted signal by this FC frequency, which is nothing but your carrier frequency. So one frequency component we are going to get at this your FC plus FM, which is analogous to the upper side frequency, and second component we are going to get is your FC minus FM, which is your lower side frequency. So this will be the spectrum of your double sideband full carrier signal, just because it is containing both these sidebands and this carrier signal, and this is the negative frequency counterparts of this particular signal spectra. So this is your upper side frequency and this is your lower side frequency. Here also, for the sake of genericity, we have mentioned this upper sideband and lower sideband, but if you have the closer look, it will not going to contain any range of frequencies. If it is containing this range of frequencies, then if you are calling them as your upper sideband and lower sideband, that will be perfect, fine, fit and fine. But in this particular case of your single tone signal or monotonic signal, we are only getting a frequency component at this particular single frequency, which is nothing but your FC plus FM. And as our lower frequency signal, or you could say lower side signal, we will be having at your FC minus FM frequency. So this is about the spectrum of our single tone AM signal. So because of the two sidebands in the frequency spectrum, it's also called as double sideband with large carrier, and in some books you will going to find it out as your double sideband full carrier signal. So the information in the baseband, or you could say information signal, or the signal without modulation, is duplicated in the LSB and the USB, and the carrier conveys no information. So obviously the three component we are talking about, this USB signal and LSB signal, both are containing the same amount of information, and the third part, as we will be having this carrier signal, which does not signify any amount of information. Information is only containing in the sidebands, that is in your upper sideband and lower sideband. So now we will going to discuss about the power distribution, or you could say power content in our single tone amplitude modulated signal. In any electrical circuit, the power dissipated is equal to the root mean square value whole square divided by its resistance. So this is very basic. That is, power will be given as V square upon R, where that V is nothing but your RMS value of the voltage signal. So in electrical circuit, we are basically performing the measurements in terms of current and voltages. So we are having this particular relationship. Hence, mathematically, the power in the unmodulated carrier, that is without performing any sort of modulation, only simply carrier signal we are talking about. And if we considering it as your in terms of voltage as your Vc cos of 2 pi fct, then in that particular case your Pc value turns out to be Vc upon root 2, where Vc is nothing but the peak value of your carrier signal, and its RMS value turns out to be Vc upon root 2. So RMS value whole square divided by R, that turns out to be Vc square upon 2R. Here this Pc is nothing but your carrier power measured in watts, Vc is the peak carrier voltage, and R is the load resistance at the antenna, you could say, and it is measured in terms of ohms. So basically we have just simply write it down as power is equal to V square upon R, where V is nothing but the RMS value of the carrier signal. Fine. So the upper and lower sidebands power will be calculated as simply from observing that generalized expression of our single tone AM signal. We can simply write it down as your upper sideband power will be equal to lower sideband power, and that will be equivalent to MA times of Vc by 2 whole square divided by 2R, simply observing that generalized expression. So that turns out to be MA square, which is nothing but your modulation index, Vc square upon 8R. So now just simply rearranging the terms, we can write down the expression for upper power in upper sideband will be equal to power in lower sideband, that will be equal to MA square upon 4 times of Vc square upon 2R. So we have intentionally write our expression like this, so that Vc square upon 2R is nothing but your carrier power. So in terms of carrier power, we can write it down the power in the upper sideband and lower sideband as MA square upon 4 times of Pc. So now if we want to check out what will be the total power, since our AM signal will going to contain three components, that is your carrier signal, your upper sideband and lower sideband. So if we are going to add up all three components, we are going to get the total power of our transmitted signal, or you could say your AM signal. So that will be equal to Pc plus power in upper sideband and power in lower sideband. So just substituting the sideband power values in terms of Pc, this Pc is P has to be in subscript, that is we are talking about power in carrier, that yields to be Pt is equal to Pc plus Ma square upon 4 times of Pc plus Ma square upon 4 times of Pc, since upper sideband power and lower sideband power are the same. So while simply performing addition of these two, what we are getting is Pt is equal to Pc plus Ma square by 2 times of Pc. While just taking the common term, this your Pc, so total power Pt turns out to be Pc times of 1 plus Ma square upon 2. So this is the generalized expression, or you could say the relationship between your carrier power and the total transmitted power or total AM power. This is very important result, and most of the numerical being asked about this particular section is from this particular formula. So just keep remember this particular relationship. So since the carrier power in modulated wave is same as the unmodulated wave, obviously the power of the carrier is unaffected by the modulation process. Fine. So now this particular figure is basically showing the AM power distribution, or you could say the distribution of power over the frequency ranges. So we'll be having this carrier frequency Fc. So its power Pc will be equal to Vc square upon 2R, and power in your upper side band frequency or your upper side frequency, that is your sideband power we are talking about, or side frequencies power we are talking about, that we have evaluated as P at USB or power in USB, that will be evaluated as MA square upon 4 times of PC, where MA is nothing but the modulation index of AM. And since the power in the upper sideband and lower sideband are same, so at the lower sideband we will be having this power at lower sideband will be equal to MA square by 4 times of PC. So please keep in mind that we have evaluated power in upper sideband and lower sideband in terms of your carrier power PC only. So since we are talking about single tone sort of amplitude modulation, so this is only a frequency term. So F USB is nothing but that will be equal to your FC plus FM, and this your F LSB is nothing but that will be equal to FC minus FM. So with 100% modulation, the maximum power in both the sidebands is equal to 1/2 of the carrier power. So what do you mean by that? So since we had already discussed about the modulation index or the percentage modulation, depth of modulation, all are similar stuff. So with 100% modulation, what do you mean by that? The value of MA, that will be equal to 1. So if we put this MA will be equal to 1, then what we are going to get is, that is P USB will be equal to PC by 4, and this LSB is also equal to PC by 4. This is what I am talking about. So if that modulation index is equal to 1, the maximum power in both sideband equal to 1/2 of the carrier power. So obviously when we will going to add up this your PC by 4 plus PC by 4, what we are getting is, that is your PC by 2. So which is nothing but the 50%, or you could say half of the maximum carrier power. So one of the most significant disadvantage of AM double sideband full carrier is with M is equal to 1, the efficiency of the transmission is only 33.33. So what do you mean by efficiency? Efficiency is the amount of wanted value, or you could say wanted power, divided by total power. So that turns out to be only 33.3% of the total transmitted signal. That is, if we are transmitting 100 watts of power, it means 33.3 watts of power would have only been actually being utilized, or are useful power, which contains the information. The less wasted in the carrier, which brings no information signal. So obviously rest of the power, that is around 67% of the power, has been wasted in terms of carrier frequency, which does not contain any amount of information signal. So this is the specification about the 100% modulation in case of single tone AM signal. So now we will going to continue our discussion, and we will going to evaluate the current calculation in AM signal. So current calculation is just analogous to as we have evaluated our power calculation. Since power in terms of voltage, we know that power is equal to V square upon R, and in terms of current, if we have to evaluate the value of power, so power is nothing but that will be equal to I square R. So we will simply going to apply that particular formula and perform the same process again. So in any electrical circuit, the power dissipated is equal to the current squared, that obviously RMS value we are talking about, multiplied with the resistance. So I square R is nothing but your value of power. So mathematically the power in the unmodulated carrier can be written as PC value, that will be equal to IC upon root 2. IC is nothing but it is the peak value of the current. So IC upon root 2 whole square times of R, that will be equivalent to IC square R upon 2. So here PC is the carrier power, which is measured in watts. IC is the peak value of current, peak value of carrier current measured in ampere, and R is the load resistance measured in your ohm. Again, from the generalized expression, the upper and lower sideband powers can be written as power in upper sideband will be equal to power in lower sideband, and its value is equivalent to MA times of IC by 2 root 2 whole square times of R. Simply applying the power formula, that is nothing but your I square R. So we have just simply applied that particular thing, MA times of IC upon 2 root 2 whole square times of R, from the generalized expression of our AM signal. So that can be rewritten as MA square IC square R upon 8. So rearranging in terms of PC, what we are going to have is, again upper sideband power and lower sideband power are same. We have just mentioned or rearranged this particular term in terms of carrier power, which is nothing but IC square R upon 2, and we can further rewrite this particular upper sideband and lower sideband power as your MA square by 4 times of PC. Just same as the previous case. So again the total power in the AM wave, so when we're going to add up all three components, we are getting this total power. So after putting the values, what we're going to have is total power that will be equal to carrier power plus upper sideband power as well as lower sideband power. So just adding these two components and taking the PC value as a common, what we are left with is your PT is equal to PC times of 1 plus MA square upon 2. This is the same relationship as we have evaluated in our power calculation case. So now how we will going to evaluate the value of total current or and your current in your carrier signal. So we just simply have to use that relationship. So PT is nothing but that will be equal to IT square times of R. Here IT is nothing but the total current and IC is nothing but your carrier current. So IT square R is nothing but your PT, and PC, instead of PC we have just write it down IC square R times of 1 plus MA square upon 2 just from this particular expression. So here the value of IT and IC, what they are signifying, you should know that these are nothing but total current and it is the current in your carrier signal. So IT is equal to IC times of under root of 1 plus MA square upon 2. So this relationship is also very important. So just keep in your memory, since most of the numerical problem would have been asked via this particular expression. Finally, we have to discuss one more term which is really important from solving numerical point of view, that is your transmitter efficiency. So this is the important term regarding the efficiency of any transmitter. So transmitter efficiency is being defined as, it is actually denoted as neta, and neta is equal to average power from the sideband, since it is the wanted power or the message basically contained in the sidebands only, or you could say information is basically contained in the sidebands only, divided by total power absorbed, you could say total transmitted power. So neta will be equal to, since messages would have been contained in your sidebands only, so P LSB plus P USB divided by PT, which is nothing but your total power. So after putting the values, what we are left with is your neta will be equal to MA square upon 2 plus MA square. So this is the finalized transmission efficiency. So the final result is quite simpler. You just simply have to put this P LSB and P USB value in terms of PC, and PT is nothing but 1 plus MA square upon 2 times of PC. So just simply rearranging that terms, you will going to get this result. Neta will be equal to MA square upon 2 plus MA square. So this is also one of the important result. So generally numerical would have been asked with this particular formula also. So in our upcoming lectures, we will try to discuss some of the numerical problems. So hopefully you will get the insight about the single tone AM signal, its power as well as current calculation. In case of any doubt, you can ask me in the comment section, and I'll try to solve it out as soon as possible. So these are the references. Thank you very much for your patience here.